This is section 2.6, and in this lecture, we're going to be talking about the main thing is going to be linear regression. Now, this is a continuation of what we saw in 2.5 correlation. Remember, correlation was the idea that you might have two different variables that are quantitative. So the example we've got here is weight as well as how much TV people are watching per week. Now, one of the things we did was when we looked at the scatter plots, you could see all like the ordered pairs. And so right here, this would be, one student, how much that they watch per week, and then what their weight is. And we said that if there is an association, we'd be able to identify what looks like the appearance of like the trend, like a linear like pattern through it. And so let's just do, what we can to try to get a line kind of goes through the middle of these dots. Now, we didn't talk about it last time, but now it's showing up today. That line that's meant to model sort of the relationship between, if you watch more TV, your weight might go up. That line is known as the regression line. And what it can do is be used to, well, if you know somebody how much they do in terms of like TV watching, you might be able to use that line as a way to predict what their weight might be. So it's known as the regression line. But more than just seeing the line, we're also going to have one of these. This is going to be the equation. And so in the equation, you've got two main variables, which are your x and your y. Think of the x as the input, or what we've been calling it ever since chapter one was the explanatory variable. It's what you're going to plug in, and then the response, we'll call that y, is the outcome that you get because of somebody's weight. This is because of someone's amount of TV watching, they might have a certain weight. Now, the other two letters that you see there are the A and the B. The A is going to be what we call the intercept. The intercept. And the B, which is the value in front of the X, we call that a coefficient. But for us, what we're going to be primarily calling it is the slope. Or you can think of the slope as the amount of change. Now, if I first were to identify for you, well, if you're looking at the graph, like where's the intercept? The intercept, I'm just going to do this, would be that. Whatever was the initial value, and then from there you see the change. So that's the intercept. It's going to be the very initial value. And again, just using this idea of how much TV someone watches, if they don't watch any TV, like 0 hours per week, then they would have some sort of weight, whatever that number is right there. The slope is going to be more of a description of, as the amount of TV increases, what might happen to somebody's weight. Here's the equation, and I think maybe this is a better way whenever you're taking notes or whenever you're doing like your reference sheet. Instead of just calling it like A and B, be more specific. A is going to be the intercept, the initial value, if someone does 0 of the explanatory variable. And then B, that's going to be the slope, how much things are changing as you go along in the graph. Now, when it comes to interpreting, what does the intercept mean? What does the slope mean? First of all, the slope is an idea of you describing for every time your x value increases by 1, there's going to be some sort of change to the response value. Now, in some studies, the slope might be positive, and some it might be negative. And so for that reason, sometimes we'll say, hey, things are increasing. If it's a negative slope, we'll say, hey, things are decreasing. But it's always for this much. For each or for every time that x increases by 1, we could talk about the slope. The intercept is the initial value, like the value that starts the whole story off. But to keep it kind of like straightforward, it's if nothing has happened, then that's what you would expect the value to be. Like sort of like an example is like a car, right? The initial value would be how much you bought it when it was brand new. But then as you drive and you put miles on it, the value is going to be decreasing, decreasing, decreasing. Now, for this introductory example about, hey, as you watch TV, some sort of change might happen to your weight. Now, here's actually the regression equation, right? This would have come through some like observational study. And the two things that we're going to intercept to interpret here first, let's just do the slope, which would be this right here. Now, anytime that you're asked to interpret a slope, here's what I would recommend that you do: make it look like a fraction, right? You can always take any number, put it over one. And so for the interpretation, it's like right here. It'd be every time that somebody watches one additional hour of TV per week, what might happen to their weight is that it increases by 0.9 pounds. So the whole idea behind this is if maybe somebody's being like a couch potato and just spending more and more time on the TV rather than walking outside and exercising, their weight might increase. So that's what we'll say for the slope. For the slope, the interpretation would be for each additional hour of TV per week, weight might increase by whatever the slope is, 0.9, 0.9 pounds. Now, if you're ever asked to interpret the intercept, that's the number that's just by itself, right? It's a fixed number. But for the intercept, it's always the idea that that's the number that starts the story off. And it would be that if someone watches no TV, so if you watch 0 hours of TV per week, weight might be 154 pounds. Right, so again, that's just our first example of how do we, what all do we want to say when we're doing a slope? Whenever we're talking about an intercept, it's these two things. Every time x changes by one, what do you expect to happen to the response? And then for your intercept, it's if nothing has happened, if you don't do any of the explanatory variable, what might be the outcome? It's whatever that number is. But let's try another one. Now, in that case, we said increase because the slope had a positive in front of it. There are going to be some situations where the slope might be negative. In this example, they were looking at these lakes and they were measuring the pH or the acidity, and then at the same time, the average amount of mercury, average fish mercury levels. And this is the equation that they got whenever they collected all the data. And you can see here the slope has a negative in front. And so, what we could say as far as the conclusion of the study is that, like, the relationship would be that every time the pH level increases by one, what tends to happen is that the mercury level decreases or goes down by 0.1523. So we'll go to put in words for each increase in pH mercury level might drop or decrease by 0.1523. They got parts per million. But I wanted to include this example because there are some situations where it's got a negative relationship, whereas one thing increases, the other decreases. So increase, decrease. Then that leaves us with the intercept, which again is the idea that if the explanatory variable, in this case, the pH level, if that's zero, or if there is no pH, the prediction would be that the average mercury, fish mercury level would be 1.53. If pH is zero, mercury level might be 1.53 parts per million. And if you're noticing that I'm using the word like might, or I might even use the words like tend, because a lot of these scatter plots or these regression equations tend to come from observational studies. So because of confounding variables or because these weren't experiment, you wouldn't use like will or like cause and effect language. You keep it more loose, more sort of like tentative, softer language. Now, in this example here, it is going to be an opportunity for us to see where are these equations coming from. It, there are formulas that you can use to calculate your slope and your intercept, but for us, it's going to be stat key. Stat key is the one that's going to be coming up with the line that best models the data that fits it. And again, it's a formula based thing to be able to get slope and intercepts. They usually call them like beta one, beta zero. But again, we're just going to rely on stat key to help us with that. Let's go to stat key, and specifically, we're going to go here to the two quantitative variables and find this study that's about cricket chirps. This is the actual data. Whenever they were recording how fast crickets were chirping, it seemed that as the crickets were chirping at a faster and more faster and faster rate, look what was happening to the temperature. So as the crickets were chirping more and more and more rapidly, the temperature also seemed to be going higher and higher and higher and higher. So there might be a relationship there, right? That as crickets chirp more quickly, it corresponds to a higher temperature. So as I mentioned, let's go to stat key. Let's look for cricket chirps. And so where we're going to go is, let me close this up. Let me get into right. I want to go right here. Let's go to stat key. We got stat key. We're going to go to this one that we were using for correlation, the two quantitative variables, very bottom one. And we're going to find the cricket chirps, which is, got to scroll down a little bit. There it is, cricket chirps, temperature versus chirps. And this is the way we want it. We want chirps down at the bottom. We're trying to see if chirps can be used to predict the temperature. Now you can click right here where it shows the regression line. That's just going to let it like toggle back on and off and leave it on there. But the main reason why we're coming here, well, first of all, look at the correlation. The correlation is 0.99. So there's like a strong relationship or a long linear relationship with how fast crickets are chirping and the temperature. But more importantly, the reason why we're here is because we want the slope and we want the intercept. There's the slope. It's 0.231. And then also the intercept is 37.679. So we're going to take both of those and we're going to just hop right back over to the lecture. And we're going to say, thank you, stat key, for, finding those for us. And so our little equation would be temperature is what we're trying to predict. And If the crickets are not chirping, it could be because this is what the temperature is. But then once they do start chirping, that's the slope. The temperature slowly goes higher and higher and higher as the crickets are chirping faster and faster and faster. So I wanted to do that one mainly just to show that on some of the homework you will need to leverage stat key and let it, it'll have the data. And then what it'll do with the data is it'll create the equation for you. Now, we haven't done this yet, but it's that you can use now the equation by plugging in a an amount of chirps, like how fast crickets are chirping, and use it as a way to predict the temperature. So what we want to do is what if the crickets were chirping at 200 chirps per minute? Well, right there, boom. That's where you're going to plug in your 200. So it's mainly just a calculator thing. Go ahead and put in your calculator 37.679 plus 0.231. And if the crickets are chirping at a rate of 200 chirps per minute, this is how you can get what might be an estimate or a prediction of the temperature. And that would be it right there. Now, the graph is there. The graph is mainly there as a way that we can verify that our calculation makes sense. Yeah, looking right here, look, there's 200. And if you go straight up, right about here, and we were to continue the regression line, and then if we look off to the side here, maybe right about there, you can see that 200 corresponds to a temperature about like 83, 84-ish. So those should reflect each other, like the same idea. Now, I intentionally, whenever I was putting this lecture together, said, let's predict 200, but that's as far as we probably want to go. Now, the last little part here says, why would it not be appropriate to maybe do 250 chirps? And kind of a short answer would be, well, the data only went up to 200. And so maybe it's, sort of like a limitation of these crickets. Maybe that's as far as as fast as they could possibly go. Maybe it's not possible for them to do 210, 220, 230, 240, or something as crazy as 250. But the word that I want you to use when you run into a question that's very similar to this is you want to avoid extrapolation, right? You want to avoid extrapolation, which is the idea of trying to do predictions that are just too far out there. Another example I can give you is, and I'll put the word. This is what you want to say in the homework. I'm sure I have it like in the answer key when you do this one. Is like avoid extrapolation, just not extending the equation too far beyond what it actually maybe is reliable for. So think of like um, think of like time. Right now it's the current, whatever current year we are right now. The time that I'm doing this video is like 2026, but back in 2020, suppose we had collected data to see how often people were going to the movies. That equation would have been probably more on the low side, that people are going to the movie because remember that was COVID, and now here we are 6 years later. You probably wouldn't want to use the same equation from the COVID year to try to make predictions for how often people are going to the movies now. It's going to be completely different now that we're 5-6 years later. But same thing from now. We wouldn't want to use equations for making predictions now in like 2030 or 2035 or 2040 because that's things can change. So in other words, these regression equations are going to have sort of like a limit to how far out you can extend. You can extrapolate a little bit, right? Maybe like 20, on this one here, maybe like 210, but maybe that'd be pushing it. Yeah, same thing if we wanted to maybe use some data from now to predict 2030, maybe. But 2040, 2050, no, you don't want to use data from now to try to make predictions for, something that's a couple decades away. Yes, you want to try to keep it as close to the observed data as you can. Um, and that's really the big bulk of today's lecture. I do have just one more thing to be aware of, which are residuals. We're not going to be focusing on like every single residual that exists within a scatter plot. We're just mainly going to be looking at calculating like one or two residuals. Now, first of all, like what is a residual? So it does have to do with the regression line and then the dots that are floating around it. So when Stackey drew this line through the dots, it purposely drew that line there as what it is offering to as the line that best fits the data. Like if I were to have done one that was like this, like that doesn't fit the data. Like I'm like way off track from what the where the dots are kind of following like a path. That right there, that line is the best line that's already through the dots. When we say that something, when there's residuals, it's that, yeah, not every dot is specifically on the line. There are some that are floating a little bit above, some that are floating a little bit below the line. And there's also some that are like way off, way above the line, and some that are way below the line. But each of those little spaces of distance between the line and the dots are residuals. So, like, for example, this dot right here, that is its residual, like how far off from the line that it is. This dot right here, that is its residual, like how far off the line that it is distance wise. But those two right there would be said to have like pretty short residuals, like not very long. Then if you look at this one, whoa, that's a really large residual. Like it's pretty far off the line. Same thing with this guy way up here. It's got a pretty large residual. Now, the other thing we can say about residuals is this idea of like how far off some of the lines are distance wise from the regression line is some of them are positive, some are negative residuals. So this one here, these two, you would say that they have negative residuals. The dot is further below the line, and then any of these up here, you would say have positive residuals. The dots are above. Now the dots, like what are these dots? The dots are the ones that were actually the original values that were collected whenever they did this study. Like the messiness, right? The line is came afterwards as a way to model what's sort of happening in terms of the relationship. So here's what you need for your notes. The observed responses are the things that actually really happened. We call those the actual values or the observed values, and we use a Y as a way to symbolize those. Those are going to be all the dots. Now, the line comes after the fact, but the line is going to be where is how you start to calculate predictions. And it's still going to have a Y, but it's going to have a hat on it. So Y is the observed, Y hat are predicted. And I already mentioned this. Those little vertical lines are the residuals, like how far off some of the dots are for, distance wise from the regression line to the observed dot. And again, the reason why Stackey put the line to be right there is because that was the line that would best do the job of trying to keep the residuals as short as possible. So it's trying to minimize those. Again, the one I did earlier, let's suppose I had done that as the line. That would have been terrible. That would have had a lot of dots that were really far off from the line. Now, here's what you're going to need to do really with this chunk of information here. You need two separate Y values to be able to calculate residuals. They've got it right here. A residual is when you take the observed value minus the predicted value. And let's go ahead and try this. So for A, this was a study. This was a study about mice and how much weight gain they were experiencing depending on how many calories that they ate throughout the day. Now, for A, when it asks to find a mouse, there was a mouse that had a really large positive residual, and it was going to want us to calculate the residual for that mouse. Well, that's going to be this one right here. That is the dot that's most furthest above the regression line. So that's the one that has the largest positive residual. Now, when I say that you're going to need two different y values, let's start with the one that's based off of the dot. So this mouse that ate 80% of its calories during the day, what was observed, I'm just going to put it right here at 17. That's how much weight it actually gained, right? 17 grams. Let's make a little note of that. The observed y was equal to 17. But now for a residual, you also need to predict it. Again, for the same mouse that had ate 80% of its calories during the day, right here, where the residual meets the regression line, you're going to use that. Look, I'm just going to put it right here at about 11. Based off of the line, that would have been the predicted weight gain for a mouse that ate 80% of its calories during the day. So you've got 17 and you've got 11. But the 11 would be your predicted. And now with those two values, you're able to calculate the residual, which I'm going to put it in words. It's always the observed minus the predicted. So it's whatever value you got from the dot minus whatever value you got based off of the line. Which would be a value of 6. And you can look like the distance from this is about a distance of 6 from 11 to 17. Now, each one of these dots has a residual. Again, we're not going to do all of them. We usually do the one that's got like the largest positive. Then we'll also sometimes do the one that's got the largest negative residual, which that's going to be that one here. It's the observed dot that's most below or furthest away from the line. And you repeat. Start with the dot. And I'm just going to go with, I mean, that's like, I'm just going to go with about 3 here just to make the math a little simpler on this. I'm just going to go with about 3. But that would be the observed, the one that was based off of the dot. Then right here where I'm putting a dot, I'm going to go with, that looks like kind of about 8-ish. That's the predicted. So you would do observed, which is 3, and the predicted, which is 8. And I'm not too concerned whether you use the correct notation for these, mainly that you do a pretty reasonable job of estimating the observed, the predicted, and then for your residual, you always take the observed minus the predicted, and we get a -5 residual. So, and what do we mean by negative? Why the negative? Why the 5? The 5 is the distance. The negative would be a way of letting somebody know that that was a residual for an observed that was lower than the predicted. Yeah. So again, you'll see an example on the homework where you can you can leverage these examples in the lecture handout. Yeah. And that really is like I think at that point that's really like the gist of the lecture. But what I want to do before we end this lecture is just do an example that kind of puts everything together. Uh, this is one about baseball, where usually it is that what they've noticed is that this is the slope, where if more runs are scored, the game might last longer. Now, this study here is a little dated. They have since the study updated some of like the rules to baseball to try to make the baseball games a little bit more exciting, more upbeat, a little more fast paced. But in terms of which is the explanatory and which is the response variable, whatever you have here on the horizontal axis, like your x value, is always the explanatory. And then your predicted is always whatever you have here on the vertical axis, and this is your response. So it'd be runs are being used to predict how long the game is going to last. And maybe this is one that if you want, you can pause the video. It's asking you for B to interpret the slope, and maybe before you do that, remember the slope is 2.529. And again, my little trick that I always recommend is just like put it over one. And so it'd be for every one of these, this is the change that you expect to have happen for the response. All right. So yeah, maybe pause the video and try interpreting the slope and look at some of our earlier examples on page 1. And then while you're at it, also maybe look at a couple of those first two examples for what do you usually need to say if you're interpreting this guy, which is the intercept. All right. Well, here it comes. All right. So it would be for every one run, the game time might increase by 2.529 minutes. For each runs scored, the game time might increase by 2.529 minutes. And then for the intercept, again, if you looked at some of the earlier examples, that's when we were mentioning zero. If no runs are scored or if 0 runs are scored, that's the game might last 158 minutes. The game. So again, I included those just as just another quick, this make sure that we are getting as comfortable as we can with interpreting slopes and intercepts. And then let's do a residual. And so that's what part E is going to be asking for, is for us to calculate the residual, which means we need a predicted value and we need an observed value. And that's what D is going to start us off with. It's going to have us calculate the predicted value or the predicted amount of time a game might last if 5 runs are scored. So at your calculator, go ahead and plug 5 into the equation. Just type it in, the 158.085 plus 2.529. And then you can round it. Yeah, you can go ahead and put it to like the nearest minute. This would be our prediction again for 5 runs. If 5 runs are scored, the game might last 171 minutes. So as I was already mentioning, the next part, E wants us to calculate a residual. And the only way you can calculate residuals is if you have a predicted and an observed. Now the predicted, we had to do a little bit of work. We had to put it on our calculator and actually like type it all in, hit enter, got our predicted. And now for the observed, that was an observed game that actually did score, where 5 runs were scored, but the game lasted 189 minutes. So this right here is your predicted, and the 189 is your observed. So the residual would be observed minus predicted every single time. And you would get a residual of 18. And I thought this would be nice for us to just to do a quick little check like, wait, where is that 18 at? If you go to the game that was just being described, where 5 runs were scored, which is right here. And there it is, straight above, there is the game that they're talking about. And if we draw its residual, you can see that it was kind of like maybe 189 was the observed, and 171 was its what would have been the predicted amount off the line. So like a distance of 18. And on the positive side, because the observed was higher than the prediction. All right, last couple things here, and then we'll call it a lesson. And I know why I included this one. It's because usually whenever we're using percentages, we might feel tempted to switch those to decimals. It's kind of like whenever you go to a restaurant and let's say you've got your bill and you're going to do a 10% tip, you don't multiply by 10. You multiply the bill by 0.10. You turn it to a decimal. Now, for this example, it is dealing with plugging in percentages. And again, it was these mice who were eating a certain percentage of calories during the day, and you could use that to predict what might be the amount of weight that they gained. And in this one, they're just giving you a heads up that if you're going to plug in a percentage, leave it as a percent, right? So here's their example. If you were doing predicting how much weight a little mouse gained if it ate 75% of its calories during the day, you would plug it in as just leave it as 75, not don't switch it to 0.75. So same thing with this one here. If you wanted to predict how much weight was gained, you're doing 50%, you would plug in 50, not 0.5. Now this is a self quiz, so I want you to go and pause the video, plug in your 50, get your predicted weight gain, but then for part B, calculate the residual. And again, that's where you take the observed and the predicted and you subtract. All right, so go ahead and pause, try this one, and then unpause, and we'll do it together. All right, so let's look at this one now. Okay, now the first part A is just taking the equation, plugging in 50, and you get 7.46 grams. Now, again, that is the predicted body mass gained. Then right here for part B, they give you the observed. Right, so it's the 7.6 is the predicted, and then right there is the observed. You just got to make sure you always do the observed minus the predicted. And if you get a negative number, that's okay. That just means that that observed was below the regression line or below the predicted value. Now, last couple little things, and I think that's the end. Yeah, last couple things is that whenever you're trying to create a regression equation and you're doing the scatter plot, you need to make sure, just like on here, you need to make sure that your explanatory variable is what you have down at the bottom. Because it is sometimes really easy on stat key to accidentally get like these two like swap, where if you were to put runs vertically and you were to put time down at the horizontal, it'll give you a completely different equation. So I think that there's going to be one where it might be in this homework, yeah, where one of the variables needs to actually be swapped. Yes, yeah, I'm pretty sure it's this one. I think it's the one with like faculty salary, but I have it in the homework mentioned like, hey, make sure like whenever you pull up the stat key, it doesn't immediately have the variable that you need at the bottom to be at the bottom. So you'll have to watch. I'll show you. I'll show you in stat key. Yeah, look at this one. This is the one that we did with the cricket chirps. And remember on this one we wanted no, not that one. The cricket chirp. Where's the cricket chirps? Right there. Yeah, we wanted crickets at the bottom because that's what we were using to try to predict the temperature. But look, if I accidentally push the switch variables and you have temperature down at the bottom, it gives you a whole new weird equation that we didn't even see before. So on the homework, when you get to the faculty salary one, you got to make sure you click on this little boop, switch the variables because you want faculty salary to be at the bottom. Okay. So the moral of the story is, um, I think I just mentioned a couple things here in the notes. I'm trying to mention this one right here. Yeah, sometimes it's necessary that you do switch the variables to make sure that here. I'll just put a little picture right here for your x. You want your explanatory to be on the bottom, and for your y, you want that to be your response. And then I'm just going to put the word not here. And look what it says. You know, if a scatter plot is only observational, you can't use those to try to claim or conclude cause and effect. You can only say this thing might be related to this other thing. Like this variable might be influencing the other. And last thing is that sometimes slopes will always be able to interpret, right? That if we were at a restaurant, every time your bill increases by $1, the tip tends to go up by about like 18 cents. But what doesn't make sense to try to interpret here is the intercept. This guy. Yeah, and imagine if we tried to interpret like that intercept, it would be that if the bill is $0, the tip is negative, 29 cents. Like that doesn't make any sense. Usually it's like you giving the the waiter waitress, a tip, a negative tip. Would that be them like giving you money? I guess like that's them giving the customer like a tip. So yeah, in those cases, like we're not even going to try to interpret it, and I won't give you one on the homework or quiz or test where you have to interpret like a weird, funky intercept that doesn't make any sense. But that's it. That is our conclusion for this lecture. It's got your residuals, it's got your regression, slope, intercept. So it's got a good little chunk of stuff in there. Stat key to help out a little bit. But I'll go ahead and end this recording. And of course, just reach out if you run into questions. Take care.